Assalamualaikum warahmatullahi wabarakatuh. We are from Group Angles and we will be presenting about the natural cooling of heated material. What is natural cooling? Natural cooling is generally defined as any technology or design features used to lower the temperature of the buildings without the use of electricity. In natural cooling, the air surrounding the object transfers the heat away from the object. Energy is transferred by natural processes in passive cooling, which are by conduction, convection, or radiation. The rate of convection heat transfer is conveniently expressed by the Newton's law of cooling, and in this video, we are going to focus on the natural cooling of warm water. Moving on to the objectives of our study, the first objective is to compute the time taken for warm water to cool down through manual and computer-aided calculation and to plot the graph using Python. The second objective is to show that the Newton's law of cooling can be used to model fluid heat convection.
So I will continue to explain about the mathematical formulation of our mini project. So first of all, the first order ordinary differential equation that we get is dt, which is capital T per dt small t, equal to minus A times As times T minus Tf, where A is the heat transfer coefficient and it is equal to 0.002 times S per meter squared, and As is the interface area between the solid and surrounding fluid and it is equal to 0.2 meter squared, and last one Tf is the final temperature and it is equal to 5 degrees Celsius. So when we substitute all the value into the equation, we will get our mathematical model with the initial condition T not equal to 80 degrees Celsius. So here is the explanation on how we get our first order ordinary differential equation. First of all, according to Newton's cooling law, you can see the equation 1. So the equation 1 shows that heat flows from TA to TB is equal to the heat flux between 2 points, which is A and B. So in the equation 2, the coefficient H satisfies the heat transformation between the solid and the bulk. Plus, according to the first law of thermodynamics, we will get the equation 3. Okay, so if we arrange the equation 3, we will get the equation 4. Then you can see that H, rho, C, and V on the right hand side are constant, so we can equate the relation of this constant with A. Lastly, it can be expressed as our first order ordinary differential equation.
Next, I will explain the manual solution, where our model is first order linear differential equation, which is dt over dt equal to negative 0.0004 times t minus 5, and our initial condition is t0 equal to 80. Next, arrange the equation in standard form. Next, take the coefficients of t as pt and take right hand side as qt from the equation 1. Then find the integrating factor and we get exponent to the power of 0.0004t. Next, multiply both sides by integrating factor and we get the equation 2. Then integrate both sides of equation 2 and solve for t to get a general solution. Then substitute t equal to 80 and t equal to 0 into general solution to obtain the value of C. Lastly, substitute C into equation 3. Thus, the temperature of warm water T at time t is given by equation 4.
Next is the computer-aided solution. By using the Python programming language, we inserted the coding shown to compute the general solution. And after running the program, we obtained the final answer, which both the manual and computer-aided calculation have the same final answer.
From the graph plotted, it can be observed that the temperature of water decreases over time, where the temperature initially starts at T equal to 80 and T equal to 0. The conclusion is it can be proved that Newton's law of cooling can be used to model fluid heat convection. The initial value problem was solved using linear method to compute the time taken for water to cool down. Since the result from manual solution is the same with computer-aided solution, then the general solution from the manual solution is verified and managed to graph the plot using Python. The recommendations of this model is to consider two assumptions to get more accurate results. The radiative heat transfer coefficient must be constant and the convective heat transfer must remain essentially constant during the cooling process for small temperature differential between the object and its surrounding.